Section 6.7, we're going to perform similarity transformations, mostly in the coordinate plane. We dealt with transformations before, but all of our transformations that we did before were congruence transformations, and they kept the same shape and the same size. But today with dilations, we're still doing transformations. We're changing a figure, but this time we're going to enlarge or reduce it. It's not going to stay the same size or shape, but it is going to be a similar figure. So the sides will still be proportional, the angles will be congruent, but not the same size and shape, not congruent anymore, but similar. So we are enlarging or reducing a figure. Now the center of dilation is going to be the very, I guess I should say the most easy point to deal with. And what's the nicest point in the coordinate plane? Well, the origin. That's going to be the center of our dilation. That's where we're going to be enlarging or reducing from, is the origin in the coordinate plane. When we talk about the scale factor of an enlargement or a reduction, just make sure that the first number you put is the side length of the image or the new figure, then compared to the side length of the original. So we're putting the new thing first, then the original. In that way, it's easier to tell whether you're making it larger or smaller, because if the new thing is bigger, then the bigger number you'll see first. If the new thing was smaller, the original was larger, then you'll see the smaller number first. So that's kind of nice. And then we do have a coordinate notation for dilations, meaning we have a notation on the coordinate plane for every point, because every original point, x comma y, is going to a new point. And you see that it's just k times x, comma, k times y. Now k is the scale factor, and that's what's important here, is that you're really just multiplying by something. If you're making it twice as big, you're multiplying by 2, so it's 2x, 2y. If you're making it smaller by half, then you're multiplying by 1/2, it'd be 1/2 x, 1/2 y. And kind of a note here, if you notice that k is larger than 1, like I just said 2x or 2y, well then it's an enlargement because you're making the new thing bigger than the original, and it's a reduction or a smaller shape if the k is less than 1, like if it is 1/2 or 1/3. Or you can do decimals, 0.2, 0.5, whatever it might be. So it's nice and it's easy to tell whether you have an enlargement, whether you're making it larger because you're multiplying by something more than 1, or whether you're making it smaller because you're multiplying by something less than 1. So talking about dilations making similar figures in the coordinate plane, let's look at an example here. Draw a dilation of quadrilateral ABCD with these vertices. Use a scale factor of 1.5 and label the image FGHJ. Remember that word image is the new figure. I'm drawing a dilation. They didn't tell me right away whether it was an enlargement or reduction, but once they say scale factor of 1.5, that means you're multiplying all of these coordinates by 1.5. You are going to do an enlargement here because of the fact that the scale factor is more than 1. My new figure will be larger. Well, let's check it out. I'm going to put my original figure out there, ABCD. A was at -6, 2. B is at 2, 4. C is at 4, 0. And D is at 0, -2. And so yes, I do have this quadrilateral here. I have the original figure now. Now, to do my dilation, I should actually find the new points. The image is going to be FGHJ. And just like back here, for the coordinate notation, you just multiply x and y by whatever the scale factor is, by k. So in this example, the fact that the scale factor was 1.5, I'm basically multiplying all of the original coordinates by 1.5 to get these new points here, by 1.5. So -6 and 2, I need to multiply both of those numbers by 1.5. Well, -6 times 1.5 would be -9, and you can check that in the calculator. Or you're thinking you're taking half of 6 and kind of adding that on, so you're adding on 3. And so we're at -9. 2 times 1.5 will be at 3. And then in the next point, B is going to become G. So we're doing 2 times 1.5, again we get 3. 4 times 1.5 would be 6. C becomes H, 4 times 1.5 would be 6. 0 times anything is still 0. D will become J. 0 times anything, still 0. Negative 2 times 1.5 would be negative 3. So these would be my new points. It should be an enlargement. It should be further away from the origin with each of these. F is at negative 9, 3. G is at 3, 6. H is at 6, 0. And J is at 0, negative 3. Let's check it out. Now, all of the lines that I draw should be parallel to their corresponding sides, since I'm going out from that origin, and any enlargement should be the case. Oh, I'm a little off there, sorry about that. But yeah, this looks pretty good. The other thing to notice is that anytime that you would do a line from the origin out through your points, they would hit both points. Like this line, dotted line, extends through both. This dotted line obviously extends through both. Here, another axis. But going through the origin, you would hit both of those points as you continue out. So something to kind of notice about an enlargement. Picture looks good. We're all set. So our first dilation in the coordinate plane. Another example here, a triangle has these vertices, A, B, and C. The image of this triangle ABC after a dilation with a scale factor of 1/2 is triangle DEF. So we're doing a dilation. This time the scale factor is 1/2, so we're doing a reduction. We're going to make that thing smaller because I'm noticing the scale factor is less than 1. It's 1/2. Sketch of triangles, verify they are similar. Okay. So I'll put triangle ABC on there. 2, 4 is A. Point B is at 8, 4. C is at 8, negative 4. It looks like I have a right triangle here, a perfectly vertical line, perfectly horizontal line. This would be my hypotenuse. I'm doing a reduction. Scale factor is 1/2. And they said the image of triangle ABC after this dilation is DEF. So my new points, D, E, and F, I'm multiplying the original x and y by 1/2, or dividing by 2. So instead of 2, 4, I'm multiplying by 1/2 for both of these, it'd be 1, 2. Instead of 8, 4, multiplying each of these by 1/2, it'd be 4, 2. Multiplying 8, negative 4 by 1/2 would be 4, negative 2. So I'll put these new points here. D is at 1, 2. E is at 4, 2. F is at 4, negative 2. Perfectly vertical, perfectly horizontal, and my hypotenuse. So again, they are similar. If I would look at those lines extended from the origin, we do hit both vertices there. From the origin, we do hit E and B, corresponding vertices, and from the origin, we do hit F and C as I extend out. Okay, so that looks good for my dilation, in this case, my reduction. I'm supposed to verify they're similar. And remember, there were 3 shortcuts that we could use to prove triangles were similar. We had angle, angle, side, 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 and side, angle, side similarity. You know, I might go with side, angle, side in this case because we definitely have right angles congruent. There's my angle congruent. Well, what about the sides around that right angle? They're perfectly horizontal and vertical, so it's very easy to find those lengths. The length from D to E was only 3 units. The length from A to B was 6. Look at that, double. The length from E to F was 4. The length from B to C is 8. And yeah, we have 3 compared to 6 is the same as 4 compared to 8. I'm looking at the sides around that right angle. So these triangles are similar by side, angle, side similarity. An angle's congruent, the right angle and the sides around it are proportional. So going back to our similarity from earlier this chapter, looking at our dilation. A real life example here, you're enlarging digital pictures. So we're making them greater. We're doing an enlargement here of some pictures. The picture on the computer screen is 6 centimeters by 6 centimeters. Oh, it's a square actually. 6 centimeters by 6 centimeters. The printed image, now we're making it larger, is 15 by 15. maybe I don't need the picture here, but it says what is the scale factor. Now, with scale factor of enlargements, you do want the larger number first because you want the new thing, the new image, to come first. You want to see whether the first number is bigger or smaller. And it is an enlargement. We're making it to 15 centimeters. Originally, it was 6. Now, 15 to 6 can be reduced. Divide by 3. And we get 5 to 2 would be my scale factor. Just remember with scale factor of a dilation to have the new thing first. It's easier to tell that it is larger in this case because the first number is bigger. So we're looking good. And the last thing I want to talk about is something you may have done in art class. Dilations are helpful in the idea that you can use like that vanishing point. So you may have drawn something at some point where you're doing some sort of perspective drawing, or you're looking down a hallway or out into the distance, or sometimes they do like down a railroad track. That vanishing point idea is really nice, and it's using dilations. If I would consider this here, this is my vanishing point, and I'm going to put an image. Maybe I'll do sort of like the Superman symbol here. Now there's my original image. Or I shouldn't say image because image is the new one, right? There's my original figure. Well, remember how I was showing that from the origin, or from that center of dilation, if you do those dotted lines outward, you can create that new picture, and all of the new points, new vertices, will be on these lines extending from this vanishing point. So I'm going through every single vertex here to help me create the new larger image. And if I do lines parallel to the original, we'll have a similar figure here. So this was the top of this straight line. So I'm going to pick a random point out here, and I know that if I go to, it would actually be this line over here, right? Because this corresponded to the vertex from this perfectly horizontal line. Now I have to go parallel to this line from here to this corresponding vertex. Right about there, I think, is parallel. And then I need to go between these and be parallel to the original. Oh man, I'm off a little bit here. Let me go back and modify this guy. Okay, and finally, from this vertex, I have to go straight down. And now you can see that I have made a enlargement of this. It actually looks pretty dang good. I was worried at first, but it looks like definitely a good enlargement of this. So on the homework too, you're going to be making some sort of enlargement using a vanishing point. But you make that line through every vertex, so then you know what line you're going to match up with, and make sure that your lines are parallel with the originals, and you're good to go. So we're talking about dilations in the coordinate plane today.